Welcome again to the Rocking Reservoir Waves on Rock Physics Driven Machine Learning series. In this second episode, we'll hear and learn more from reservoir expert Jyoti, the intricacies of this integrated rock physics driven machine learning workflow. To recap, if you missed out our first episode, we explored into the world of machine learning and its application in oil and gas, specifically focusing on reservoir characterization and the challenges posed by limited data. Hello again, Jyoti. So, in our previous conversation, you introduced the concept of using rock physics to generate synthetic catalogs. Could you please elaborate on this process?
Thank you for having me, Ayan. As we discussed last time, our deep machine learning efforts can be hampered by the scarcity of the labeled data. So to overcome this limitation, we employ rock physics to simulate various scenarios within the geological formations. You see that within a drilled well, we have recorded elastic properties like sonic velocity, shear sonic, and density. Additionally, we have also interpreted for petrophysical dataset like porosity, water saturation, and volume of clay. And we also know some more information about the subsurface like temperature, pressure, laboratory measurements like bulk and the shear moduli for various minerals. So using all this information together, we build a rock physics model, widely known as RPM. This RPM is a set of equations relating the reservoir properties to the elastic properties. And by utilizing this RPM, we estimate elastic properties and compare those with the one measured in this drilled well. This validation process of comparing our predicted versus the measured elastic properties helps us to fine-tune the rock physics model to accurately represent our field conditions. Now, in addition to the RPM, we also have access to statistics like reservoir properties and elastic properties in the drilled well, which includes the background trends, vertical variograms to assess vertical variability, and covariance information to understand the interrelationships between different reservoir properties like porosity, saturation, or volume of clay. Now, armed with these statistics and rock physics model, we can model elastic properties for various scenarios within the reservoir layers. Using the rock physics model, we can simulate how elastic properties like sonic velocity, shear sonic, and density would behave under different reservoir conditions. For instance, we can model what happens if the sand thickness increases to, let's say, 40 meter or 50 meter, or the porosity drops to 10%, or oil saturation drops to 20%. This enables us to generate synthetic elastic logs corresponding to a wide range of field scenarios, which might be present somewhere away from the drilled well location. And we don't know yet because we haven't drilled those wells. So with this, we can create hundreds of these synthetic wells, each representing a unique set of geological conditions. And with this synthetic catalog with hundreds of wells generated from a theory-based rock physics model method represents the possible scenarios in our field. With this, now we have ample amount of data to train a neural network, or for that matter, a deep neural network. I must say, Ayan, that this powerful methodology differentiates us from our competitors. By creating many synthetic wells, we have practically expanded the labeled data pool. It is a key step in enhancing our deep machine learning capabilities in the realm of reservoir characterization.
Thank you, Jyoti, for the detailed explanation. After we generate hundreds of synthetic wells, what comes next in our workflow?
Ayan, once we generate hundreds of synthetic wells, we will use a real seismic wavelet to model AVO response for each of those synthetic wells. Now, this wavelet can be a single wavelet, or we can also use angle-dependent wavelets to ensure the accuracy of our AVO responses. This comprehensive dataset will now serve as a synthetic catalog and will be instrumental in our deep machine learning training models. Essentially, what we have done, we have created a collection of labeled data in 1D format along with the collection of possible AVO responses, and that correspond to our geological setting.
So once we have a large amount of label data in the form of synthetic wells and their corresponding AVO responses, which deep machine learning algorithm will we be utilizing?
Here in Hampson-Russell, we are using convolutional neural networks, popularly referred to as CNN. CNNs are widely recognized for their prowess in image classification applications across various industries. Think about the facial recognition technology in our smartphones. It relies on CNNs for accurate identification. The key requirement for successful image classification technology is the large amount of labeled data for training. And in our case, by using rock physics, we have already met this prerequisite by generating hundreds of geological scenarios representing our subsurface conditions. So leveraging the CNN algorithm, we will train the neural network on our synthetic dataset, perform a transfer learning using real seismic data, validate its performance, and then apply this trained model to 3D seismic data to predict multiple properties of our interest, and that too simultaneously.
Now, Jyoti, in your last sentence, you mentioned the ability to predict multiple properties with CNN in one go. Can you clarify this further?
Certainly, Ayan. Indeed, one of the significant advantages of using CNNs is the capability to predict multiple properties simultaneously, up to a maximum of 5 properties in our software, Hampson-Russell. This is a key strength that significantly reduces the project's turnaround time. Let's say that we are interested in predicting 3 reservoir properties: porosity, water saturation, and volume of clay. So unlike the traditional machine learning methods that we discussed in our previous episode, where we would typically train separate models for each property, here using CNN, we train the neural network to predict all these 3 properties in a single training process. This efficient approach can substantially accelerate our project timelines because we are doing multiple things together. I believe that the ability to estimate multiple reservoir properties from seismic data, and that too in the early stage of a field development life cycle, add another dimension to our conventional amplitude interpretation.
Jyoti, you just said adding another dimension to interpretation. Can you explain this more detail?
Sure, Ryan. When I say adding another dimension to interpretation, I'm referring to our traditional seismic interpretation practices. Traditionally, we primarily interpret seismic data based on amplitudes. It can be a zero offset seismic amplitude or AVO attributes like intercept and gradient. And then we often create maps to visualize the spatial continuity of geological events. However, with the capabilities of CNN and machine learning, we can go beyond amplitude interpretation. When we have a volumetric model that predicts properties such as porosity and water saturation, you see that our interpretation can be more sophisticated and direct. Instead of solely interpreting amplitudes, we can interpret the data in terms of reservoir properties. This means that the interpretation process transforms and we are no longer limited to just looking at the amplitude variations. In essence, having the ability to estimate reservoir properties early in a field's life cycle allows us to generate more meaningful maps and interpretations directly related to reservoirs' physical properties. This has the potential to revolutionize how we analyze and interpret seismic data, especially the AVO data.
I see. So before we talk about the interpretation and technical details of CNN, I am reminded of the convolution we use in seismic data. Is the convolution in CNNs the same as seismic convolution, or are they different?
That's a very good question, Ayan. Convolutional neural networks are indeed named after the mathematical operation called convolution, which is fundamentally the same operation used in signal processing in geophysics. Typically, the convolution operator involves a one-dimension series, and the Earth filter models the series. The operator used is usually quite long, often consisting of 20 to 50 time samples. On the other hand, CNNs makes use of two-dimension or higher dimensional convolutional operators. These operators are typically quite short, like 3 by 3 or 5 by 5, but are cascaded. And since the operators are cascaded, their effective length is longer, but still shorter than the typically used ones in the day convolution. Since both share the same mathematical operators, this helps the CNN capture the physics of seismic data.
Thank you very much, Jyoti, for clarifying that. Coming back to interpretation, can you share an example where you applied interpretation of seismic amplitude alongside reservoir properties derived from rock physics-driven machine learning and witnessed a significant improvement in interpretation?
Absolutely, Ayan. I can provide you with an example from a case study, and in fact, we have published this as a conference paper as well. The case study I'm referring to is from the West Trial rocks data from the Carnarvon Basin, offshore Western Australia. In this region, the shales are of middle to late Jurassic age, and the sands are mainly medium to coarse grained with good porosity and permeability. In terms of data set, we had 2 wells in the study area along with AVO seismic data and the interpreted horizons. Like I discussed about the methodology, we started our approach by building a rock physics model based on one of the well. Using this rock physics model and the statistical data set, we simulated various geological scenarios for parameters like porosity, saturation, volume of clay, and reservoir thickness. This process generated over 200 synthetic wells, each with corresponding elastic properties reflecting different reservoir simulations. We then conducted AVO forward modeling using these synthetic wells and a real-world seismic wavelet. This resulted in having hundreds of synthetic wells in 1D format and their AVO responses presented as seismic images. So practically, we have prepared our data set for a deep machine learning algorithm. And this is where we started our deep machine learning algorithm, which is convolutional neural network in this case. So we trained the CNN and built an operator using synthetic data set first, and then further refined the training through the transfer learning technique. Using CNN, here in this particular case study, we predicted 4 properties: acoustic impedance, volume of clay, porosity, and water saturation. And then for interpretation purpose, we created maps for different sand intervals. Now let me provide you with a specific example related to one of the sand interval, which we will call as M sand. When we examined the seismic attribute map, it revealed 2 zones with favorable amplitudes. One zone, which had 2 drilled wells, penetrated the reservoir sand, and it gives us confidence about the amplitude in that particular zone. However, the other zone had no drill well data. Despite this, it exhibited a similar amplitude signature to the hydrocarbon-filled zones with proven wells. So based solely on the interpretation of seismic amplitude, one might assume that this other zone also contains hydrocarbon-filled sands. However, when we analyze the maps of volume of clay, porosity, and saturation, then we found that this other zone had high volume of clay, poor porosity, and that too filled with brine. So you see that this kind of interpretation, combining seismic amplitudes with reservoir properties, helps us significantly reducing the uncertainty in prospect identification. It has demonstrated the power of integrating machine learning derived reservoir insights with traditional seismic interpretation, and thereby offering a more comprehensive understanding of the subsurface conditions and minimizing exploration risk.
Thank you, Jyoti, for sharing your experience and insights. The technology indeed appears promising. I already have questions about CNN. However, I will park those questions for our next episode. Thank you so much, Jyoti, for your time.
Thank you, Ayan. Thank you for having me.
And that brings us to the end of the second episode on rock physics-driven machine learning. We hope you enjoyed our exploration of how advanced data-driven algorithms and artificial intelligence are enhancing our understanding of rock properties and reservoir behavior. Thank you for joining us. And if you have any further questions or topics you'd like us to cover in future seasons, feel free to reach out to us. Until then, keep rocking and keep exploring.